Hi guys, welcome to our channel 10 power 100. So I hope you all are doing good. Okay, so today I have taken most important part in our physics, that's our derivations. As you all know, it's like a cream on a cake, okay? So it's a most important part in physics, and if you know to derive in a most simplest way, I think that's something where the first step you have climbed in your physics preparation. Okay, so that's the main reason why I've taken the derivation, like list of all the derivations from the current electricity chapter for now. Okay, why? Because current electricity chapter is something a high weighted chapter in physics. So that's the main reason why I've selected from this. So almost all derivations I've tried to cover, and in a most simplest way. I hope you find this useful. Okay, and so for all your preparation, please follow our channels. Please subscribe, like, and follow our channel. Okay. Fine. What is drift velocity? Derive an expression for drift velocity of electrons. Okay. So this is a derivation. They can ask you what is drift velocity also. Okay. So as you know that normally a conductor, okay, I have taken a conductor over here. In a conductor that electrons will be there, right? Randomly they will be moving. Okay, without applying the electric field. Once you apply the electric field, what happens? They start moving in one particular direction. So that's what velocity, with what velocity they got drifted is called as drift velocity. So you will have to define what is drift velocity. Basically, drift velocity is what? The average velocity of an electrons moving towards the positive terminal. Okay, that's the meaning of drift velocity. So this is the expression for, I will be deriving the expression for drift velocity. So you'll have to write all these things first. Like when a conductor is subjected to the electric field, each electron experience a force. Okay, so what's that force here? So F equals Q times E. Okay, since we are dealing with the charges, we all know the force formula, right? The electric force formula. So F equals Q times E, where the charge what we are taken is electron. So instead of Q, I'll take minus E times capital E. So take this as first equation, guys. Okay, so take that as first equation. So how much electron that how much force that electron experiences, that is given by the first. Next, as you know, there are from Newton's second law we have that F equals m times A. Okay, so from here, what is the what is the acceleration it acquired? So A will be equal to F by m. Okay, one second. Okay. So take this as equation 2. Okay, now let me equate 1 and 2. You can just mention here, equate 1 and 2. So when you equate 1 and 2, you will be getting m times A equals minus E times capital E. When you equate 1 and 2, you get ma equals minus E times capital E. So what is the acceleration acquired here? Acceleration will be equals to minus E capital E by m, guys. So let me take this as equation 3. Okay, so this is the acquired acceleration. Okay, so first I took force equals the electric force formula, and then I took a Newton's second law. From that I equated, because both are force, right? We can equate 1 and 2. I got what is the acceleration experienced by each electron. Okay, so you can just mention m is mass of the electron, E is charge, and E is electric field, guys. Okay, then you can just take from our equation of motion. You all know the equation of motion, right? You would have learnt in grade 9. Okay, so from equation of motion, we know that V equals U plus AT, guys. The basic formula, V equals U plus AT. So here, initial velocity means what? Like all the electrons without application of electric field, they'll be moving in a one particular velocity. That's the reason we say the initial velocity will be equal to 0. Okay, and A, we already have got A equals minus E capital E by m, and then T can be considered as tau, guys. What is the meaning of tau? Tau is the average relaxation, it's a relaxation time. Okay, the relaxation time is denoted by tau. So what is tau means? It's the average time difference between the two consecutive collisions, okay, is known as the relaxation time. You can just mention there. So T can be taken as tau. Now when you substitute, you get V, you can take as drift velocity, U is 0 plus A. From third equation we have got that minus E capital E by m, and in place of T we write it as tau. Okay, so finally what's the drift velocity expression? Vd equals minus E capital E by m times tau. That's it. So hence proved. That's it, guys. So this is a 5-mark derivation. So please draw the diagram. So sometimes they might give like a 1 mark for diagram might be there. So that's the reason, write the diagram, and I've already written over here, right, a bit story I will have to write it, like consider a conductor which has electrons which experiences a force, all that you'll have to mention that. But these are the basic steps. Okay, so first take equation 1 and 2, equate, then you will get acceleration, then substitute an equation of motion formula. That's it. Okay, the most simple derivation. Fine. Now let's move to the next question. Derive an expression for current in terms of drift velocity, or they can ask you prove that I equals NEA VD. Okay, anything they can ask you here. Even here the same diagram, you can just tell that consider a conductor of length L, area of cross section A, and N is the number of electrons per unit volume. Okay, so if small l is number of electrons per unit volume, we have here total many number of electrons, right? So you can just consider here the total number of electrons. Okay, the total number of electrons. Okay, capital N, I'll take it as capital L, will be equal to number of electrons times the volume of the conductor, guys. Okay, so capital N is what? Number of electrons per unit volume times the volume of the conductor. Okay, now since volume, how to take a volume from the diagram here? Volume can be taken as area times length, right? So I'll just substitute here as NaL. Okay, so capital N equals what? Small n, and volume is taken as area times length. Okay, so why I have taken as number is because I need to prove I equals NEA VD. From N, let us connect to current, guys. Okay, now we got what are the number of electrons. Now let us find out what is the total charge on it. Okay, so we'll come from the stepwise. So first we found total number of electrons. Now let us find what is the total charge. So total charge, I'll denote it as capital Q. Capital Q equals capital N times E. We all know the formula, no? Q equals N times E. So capital total charge equals capital N times E, where capital N is what? Small n A L times E, guys. So this is the total charge. As I said, I want to find current. So first I found total number of electrons, then I found total charge. Now what's the final step, guys? Let me find out what's the total current. Okay, so the total current equals, I can just mention here. So the current is given by the formula I equals what? Q by T, right? So we already found Q. So what is Q, guys? Q equals N A L E divided by T. Okay, so we have got I equals N A L E by T. Still we are not yet done. We have to find current in terms of drift velocity, right? But we don't have any velocity over here. But still we have a length by time, guys. So already we know that length by time or distance by time can be taken as what? Velocity. Here we are taking it as drift velocity. So we'll denote it as Vd. Therefore I equals what? N A E. In place of L by T, you can write as drift velocity. That's it. Hence proved. So again, this is one of the 5-mark question, or it can be asked for 3-mark also. There are possibilities of asking for 3-mark as well, but most important question or derivation. Fine. Chalo. Now let's move to and yeah, they can ask in terms of anything like how current depends on a drift velocity, or in based on this there can be an application question like now I'll increase the current, what happens to the drift velocity? So you can see here in a formula we have current is directly proportional to the drift velocity, right? So as you increase the current, what happens? Drift velocity of electrons also increases. Okay, so remember the formula. In the formula itself you will find like n number of questions like application questions or in MCQ questions. There are many questions based on this. Okay, chalo. Next move to the next question. Deduce the relation connecting the current density, where we know current density is J, and conductivity is sigma of a conductor. Okay, or this can be asked as a derive the relation J equals sigma E. Okay, or derive the relation between current density and electric field. Yes, current density means J, electric field means E. Or it can be asked as obtain the expression for conductivity in terms of relaxation time. Okay, fine. I think almost all are like interrelated over here. Fine. Now let us prove this now. J equals sigma times E. Okay, here to prove this I have 2 different methods to prove this. You can follow either method. Okay. Okay, so the first method, this is the first method, like either you can just refer. So first let me take here as, so you can just mention the relation between current and the, okay, the relation between a current and drift velocity is given by, okay, the relation between current and drift velocity is given by So what is the relation, guys? I equals, just now we proved it, NEAVD. Okay, let me take this as equation 1. Also we know that drift velocity is given by the formula E, capital E by m into tau. Take this as equation 2. Now just substitute. Okay, substitute 2 in 1. Okay, substitute the drift velocity in equation 1. You will get I equals NEA. Instead of VD, write E, capital E by m into tau, guys. Okay, instead of VD, I replaced VD by this. Now, yeah, I can multiply N. E into E is E square, A, E by m into tau. So I got this much. Still we are not yet done, right? Because we have to get current density. So where do I find current density over here? Current density is what? Current per area. We all know that. You should be knowing that. Current density is what? Current per unit area. Okay, so I have current here, but I have area on the other side. So what I'll do is I'll bring this area to this side. So it becomes I by A equals N E square, capital E. I'll write tau by m over here. Now, what is this I by A, guys? I by A is J. Okay, I got my LHS. And on the RHS, you have sigma times E. You already have E. Write down E. So, this complete remaining term will be sigma. Hence, proved, guys. That's it. Okay, so this question can be asked in a different way. They can ask you prove equals sigma E, or they can ask you prove what is that, write the relation between a current density and electric field. So in any ways they can ask you, where you can write here where sigma equals what? N E square tau by m, guys. That's it. Okay, and this question can be asked like prove sigma equals N E square tau by m. Okay, in case if they ask you that, then again the same derivation itself. But for this derivation, you will have to remember the first two formulas, like first two derivation formulas. In case if you can't remember the first two derivation formula, I have another method to do this. So very simple method, that's from Ohm's law. Okay, so Ohm's law, I think everyone can remember the Ohm's law formula, right? It's a basic formula in physics. So Ohm's law states that potential is directly proportional to current. So we take it as V equals Ri. Okay, so that's the equation 1. Next, from resistance, we have a resistance formula. Again, this you learnt in grade 10. So what's the resistance formula? It is rho L by A. I'll take this as equation 2. Now, substitute equation 2 in 1, guys. Okay, in case if you are finding it very difficult to remember this, then easily you can remember this, right? V equals Ri, where R equals rho L by A. Now substitute 2 in 1. In place of R, write rho L by A times I, guys. Okay, now what is my question here? J equals sigma E. Wherever you see I by A, directly you can take it as what? J. So I by A is what? J. That is nothing but current density. Now I want J equals sigma E. So what I have to do? I have a J here. So what you do? Move this rho and L to the other side. So when you move, what happens? I'll take J on the LHS. J equals V. On the RHS we have V divided by rho times L. So that's how the transition happens, right? J equals V by rho L. Now what is voltage per unit length, guys? Okay, so the voltage per unit length is taken as what? Electric field, where you know that V is equals to E into D, or E equals V by D, or you can also take V by length of the conductor or distance moved by the electrons. Okay, so in place of V by L, I'll take E. And what is reciprocal of rho? Rho is what? Rho stands for conductivity. Rho stands for resistivity, right? So reciprocal of resistivity is what? Conductivity. That's it. Hence, J equals sigma times E. Hence, proved. That's it. Okay. So if you find any method, like whatever is comfortable, you can do that. Okay. So I think yeah, both you'll get 5 marks. Don't think the derivation is quite small. You might not get a 5 marks. Yes, you will get it. But please write something on it, like from Ohm's law, or try to fill the paper, because presentation matters a lot. Okay. See, I can derive any derivation in 2-3 lines. I can complete the derivation. But how can we give a 5 mark for just for 2-3 lines, right? Even for an evaluator, it will be very difficult. Now the answers are correct. So that's the main reason presentation matters a lot. So that's the reason, try to complete fill the paper over here. Okay, fine. Now, and yeah, one more thing you should be knowing, that this stands for conductivity. Okay, so conductivity is reciprocal of what? Resistivity. So if you know this, again, you can see the fourth question over here. Obtain the expression for conductivity in terms of relaxation time they have asked. So based on this only, you can again obtain the relation for that. Okay, fine. Now moving to the next question. Okay, so again, this is one of the most important question. That's EMF, what's that? Cells in series. Okay, so first I've taken cells in series, then we'll move to cells in parallel. Okay, so as I said here, the equivalent EMF and internal resistance of two cells in series, guys. So let me draw the cells over here. So draw the cells as they are connected in series. So cells will have EMF E1, R1, E2, R2. As you all know, the same current flows across the cell, okay, across the cells in series. So now let me take this point over here as, I'll take this point as A, B, C. So this potential, I'll take it as VAB, because in a series the potential gets divided but current remains the same. Okay, whereas in parallel, current gets divided but potential remains constant. Please know this point. So here we have taken series, that's the reason current is constant, whereas potential is getting divided as, I'll take this potential difference between point AB, I'll take as VAB, potential difference between BC, I'll take it as VBC. Okay, and the total potential, I'll take it as what? VAC, because it's a point between A and C here. Okay, now for this, to derive this complete two derivation also, you need to know a formula, that is V equals EMF E minus I times R. Okay, so you need to know this formula. Now let me find out what is VAB, guys. So what is VAB? VAB is across a point A and B, right? So that's the reason in place of E, you can take it as E1, I will be the same. In place of R, you will take it as R1. Okay, similarly, right for VBC, VBC can be taken as E2 minus of I times R2, guys. Okay, so I found what is the potential between AB and between BC. Now find total potential, that is VAC. So what is total potential? It is nothing but VAB plus VBC, where VAB is taken as E1 minus of I times R1 plus E2 minus of I times R2. Okay, now just arrange this formula, E1, E plus E2, I'll bring it together, minus I R1 minus I R2. Okay, now again let me arrange this formula as E1 plus E2, I'll take minus I common over here, I'll get R1 plus R2, guys. Okay, now I got the total potential. Now the main step is compare with our main equation. That is, as I said, remember this equation, right? R. Okay, so this is a total potential. So total EMF, I'll take it as equivalent EMF. Total internal resistance, I'll take it as equivalent internal resistance. When you compare this with the other equation, okay, you can just mention this as equation 1 and the finally equation 2. When you compare 1 and 2, okay, when you compare 1 and 2, what are you getting, guys? In place of E equivalent, what do you have? You have E1 plus E2, right? So E equivalent is given as E1 plus E2, whereas R equivalent, check here, minus I. Okay, in place of R equivalent, what will you get? You will get R1 plus R2. That's it. So when two cells are in series, what happens? The equivalent EMF will be sum of EMF and equivalent internal resistance will be sum of internal resistance. Okay, it's not only for two cells. You can draw, derive for other like 3-4 cells also. No problem. But same thing, you will get sum of here. Okay, you'll get an algebraic sum of EMF and algebraic sum of internal resistance. Okay, that's it. This completes the derivation. Yeah, again, it's a very small derivation, but it can be asked for 5 marks, or sometimes they can ask it for 3 marks also. Okay, fine. Now, that's it. Now, the same methodology, let us move for parallel, guys. Okay, so this is all about the series. Now, we'll move to parallel. So, if you are drawing a parallel, draw the cells in parallel over here. Okay, you can just draw like this. Yeah, you can draw a long line, shorter line also. In case you can draw two parallel lines also, no problem. Okay, but some people will get confused because this is a symbol of capacitor also. Okay, so that's the reason you need not get confused over here, and don't worry about all that. Okay, now as I connected in parallel, so this particular cell will have EMF E1, internal resistance R1. This cell will have EMF E2, internal resistance R2. Here current is not constant. Okay, current gets divided. So now total current, if I consider this as point A and this as point B, now the current get divided as I1 and I2. Okay, so the total current is what? I1 and I2. Again here you will have to remember the potential formula, guys. That is V equals E minus of I times R equivalent. Okay, so again remember the main formula. V equals E minus I times R. Now for the first cell, okay, I'll take this as cell 1. For cell 1, what's the potential, guys? Potential for both the cells are same, right? Because they are connected in parallel. I had mentioned this. So don't take V1, V2, just take it as V. In place of E, take it as E1. In place of I, take it as I1. And in place of R, you will take it as R1. This is for first cell. For cell 2, again, V will be the same. In place of E, I'll take E2 minus of I2 times R2, guys. Okay, so from this equation, what is I1? I1 equals what? If I move this I1 R1 to the other side, you will get I1 as E1 minus of V by R1, guys. Okay, similarly, I'll get I2 as what? E2 minus of V by R2. Okay, now here current is getting divided. So that's the reason I'll take the total current as I equals I1 plus I2. Okay, so now in place of I1, I'll write E1 minus V by R1 plus I2 as E2 minus V by R2, guys. Okay, now again, it's all about arranging the formulas. Okay, so now I'll put EMF in one side, the voltage on the other side, current on the other side, so that finally I can compare with my main equation. That's V equals E minus of IR. Okay, so that's what you have to do. Finally, you have to compare with our main equation. Then easily you can find out what is the equivalent EMF and equivalent internal resistance. Fine. Now it's all about the arranging. So I will take this E1 by R1 plus E2 by R2 minus V by R1 minus V by R2, which is equal to I. Fine. Now, now E1 by R1 plus E2 by R2 minus V, take it as common, you will get 1 by R1 plus 1 by R2. Fine. Now, can you compare with our main equations, that is V equals E minus IR? No, right? You can't compare. So again, let me do some arrangement over here. So what I'll do is this complete V, I'll move to the LHS, guys. So what will I get? I'll get V of 1 by R1 plus 1 by R2. Okay, because minus when it goes here, it becomes plus. Remaining you write as it is. E1 by R1 plus E2 by R2. Okay. This plus sign, when it moves the other side, it becomes minus I, guys. Okay, now almost I can compare, right? It is almost comparable, but still not. So now I need only V on in my LHS. So that's the reason this complete thing I'll shift to the other side. So what happens? V equals, okay, so E1 by R1 plus E2 by R2, write this as it is, minus I, write this as it is. Whatever was next to V, when you shift, it goes to the denominator. So what was next to it? 1 by R1 plus 1 by R2. Same thing you write to the other side also. 1 by R1 plus 1 by R2. Because it's a subtraction. When you are moving, it goes to, for both it goes, right? Now yes, almost I can compare. Again, let me rearrange this by using the LCM and all. So what happens when I take a LCM of this? R1, R2. I'll get as R1, R2 LCM. So what will be this term? E1, R2 plus what will happen here? E2, R1, right? So divided by, again 1 by R1 plus 1 by R2 LCM is what? R1, R2 is the LCM. On this side, what will you get? R2 plus R1 or R1 plus R2. Yes, after LCM. Minus I. So this complete term, again if I'll just take it as divided by, I'll take R1, R2 as my LCM. So what will I get here? R2 plus R1 or R1 plus R2. Okay. So what you can do here, you can delete R1, R2, R1, R2. Okay. So finally you will get V equals E1 R2 plus E2 R1 divided by R1 plus R2 minus of I. When I reciprocate, what I get? R1 R2 by R1 plus R2, guys. Now it's easy for me to compare with my main equation. Okay, when I compare this with my main equation, so what's my main equation over here? My main equation is V equals equivalent EMF minus of I times R equivalent. So that's what they're asking here, right? What is a final equivalent EMF? Leave put all that, two cells connected in parallel, all that. You just focus on what is it connected? Parallel it is connected. What are you supposed to find? Equivalent internal resistance and EMF. That's it. Focus on these things. Remaining, they might tell some stories and all. Leave about all that. Just check whether it is series or parallel. Series means you will do the previous derivation. Parallel means you will do this derivation. Now whatever equation you got, compare with this. You have got to R1 plus E1 R2 divided by R1 plus R2 minus of I R1 R2 by R1 plus R2, right? Your previous equation was this. Now when I compare with my main equation, what is equivalent EMF, guys? Equivalent EMF equals E2 R1 plus E1 R2 by R1 plus R2, whereas R equivalent is R1 R2 by R1 plus R2. Hence proved. That's it. It's quite long, but it's very easy, guys. Okay, so this chapter, I think it's like most easy derivations you have, and you know, like derivations for 15 marks you have in like 5 marks there, and for 3 marks also they can ask you the derivation. I think it's better to almost practice all the derivations. Okay, so this completes the derivation. Hence proved. Okay, that's it. Fine. Now let's move to the last derivation of this chapter. Again, it's very easy derivation. Okay, now here they have told using Kirchhoff's law. As you know, in this Kirchhoff's laws are very important. Okay, practice all the laws as well. Okay, so here we have two Kirchhoff's laws, right? What are those two laws? One is Kirchhoff's current law. Okay, I'll revise laws also here because I need the laws. They're telling using the law arrive at the condition. Of course, to arrive at a balancing condition, you need that law. Okay, so from that Kirchhoff's current law, I'll write it as KCL. So where KCL is also known as what? It is a junction rule, guys. Okay, so what KCL rule states is sum of current entering the junction will be equal to what? Sum of a current entering the junction will be equal to sum of the current leaving the junction. Okay, because here there is a conservation of charge. Okay, there is no charge is neither created nor destroyed. Whatever current is entering will be equal to current leaving the junction. That's what is Kirchhoff's current law. Okay, I will not take all that. Next we have Kirchhoff's voltage law, right? Okay, Kirchhoff's voltage law. For this, you should be knowing the sign conventions. Okay, while deriving, I'll teach you the sign convention in a quite easier way. Okay, so please pay attention here. So to prove this derivation, first let me draw a Wheatstone network. Okay, so let me draw a network over here. This is a resistor. They're connected in the form of a bridge. Okay, so that's the reason we call it as what? We call it as Wheatstone bridge or Wheatstone network. Okay, in the middle of two resistors, we will place a galvanometer. The other two, you will connect it to what? Battery. Okay, now let me name this resistor as P, Q, R, S. Naming matters a lot over here. Okay, so PQRS, and then you can name it as R1, R2, R3, R4 also. If not, you can name it as PQRS. Now from the battery you get a current. Total current is I. Current enters the junction. So this is a junction, right? I'll name this junction as A, B, C and D, guys. Of course, I should correct this. Now when the current enters, what happens? Current gets divided as I1 and this current is I2. Now, as it goes to the point, again it gets divided. Through galvanometer, Ig current flows. you can denote it as Ig. The current which flows through the galvanometer, you can take it as Ig, and then which current which flows through the Q is taken as I3, you can take it. Now, because the same current will not go here because it's all parallel connection over here. Okay, now I1, Ig, I3 will go over here. I2 goes over here. Now, what happens here? I4 current goes over. Okay. Okay, fine. The current I4 goes over here. And then what happens when it reaches the junction there? The same current comes back. Fine. Now, as I said, from Kirchhoff's current law, what you can do is I can take a junction, guys. So you can see at a junction B, okay, you can say from Kirchhoff's current law, or we'll mention it as using Kirchhoff's current law. Okay, I think that's the best point. Okay, or apply Kirchhoff's current law at the junction. What's a junction? At junction B, guys. So let me apply a Kirchhoff's current law at junction B. You can just take that junction B. You can see I1 is entering the junction, I2 is leaving the junction, I3 is also leaving the junction. So what this law states, current entering the junction I1 is equal to sum of current leaving the junction. So what are the junction leaving? That's I3 plus Ig, guys. Okay, so from this I will take I3 is what? I3 is equals to I1 minus of Ig. Okay, let me take that I3 like that. Similarly, find out, same, apply a current Kirchhoff's law at junction D. Okay, when you apply, look at the junction D over here. Ig is entering, I2 is entering, whereas I4 is leaving the junction. So you can take I4 as what? I2 plus Ig. Okay, so first Kirchhoff's current law I applied. Now moving to the Kirchhoff's loop rule. So for that we should see the loop. Now I'll take one loop as this and the other loop as this. Okay, so the loop 1, apply Kirchhoff's voltage law for loop. Loop means like a form, it's like a combination of resistors in the form of a loop. Okay, so that loop I'll name it as A, B, D, A. So let me complete that, A, B, D, A. Okay, so how to apply a Kirchhoff's voltage law means, see, well, remember the sign convention, what we do is, whenever, now suppose I am going in this way now. Okay, if I am going in this direction, if a current is along my direction, okay, then we take negative sign. Please remember that. Okay, if I am going in one direction and if current is also on the same direction, then you will take that as minus of I times R, guys. That's a sign convention. Now, if you are going in this direction, if a current is opposite to you, okay, if a current is opposite to you and you are going in this direction, okay, as I was telling, if I am going in, okay, 1 minute, fine. Now, if I am going in this direction and if a current is opposite to me, then what happens, then you will take it as plus of I times R. Okay, I don't know, it's not letting me to write over there. Fine, I hope you understood that. Again, I'll repeat. Okay, so if I am going in one direction, if a current is also in the same direction, then we'll take it as minus of I times R. Okay, that's what is loop rule. You might be knowing that. In case if I am going in one direction and if a current is opposite to me, then I'll be taking it as what? Plus I times R, guys. So please remember this. Let me just delete this. I hope you understood. Now let me apply the rule. Now I am going, I am going means how you are taking the direction. That's what it meant. Okay, now I am going from A, B, D, A, guys. Okay, so what was this? Something is wrong today. Okay. Okay, so this is P and this is I1. Okay, now I'm going in this direction. Current is also along with me, right? So what you take? You take it as minus. Current is I1 and what's the resistance there? P, guys. So that's how you write it. Okay, I'm going like this. Now again I'm coming like this. Current is also along with me. So you take minus of Ig times. What's the resistance here? G. Even galvanometer will also act like a resistor. Now I went like this. Okay, now I'm going like this, but current is opposite to me. So what will you take? Plus I2 times R equals 0. Don't forget to write equals 0 because you completed the loop over there. Okay, I hope you understood. Now you try for the loop, another loop. What's a loop? However you want, you can take. You can start from D, B, A, B, D also. Anything is fine. Okay, it need not be in one particular pattern over here. However you want, you can take, but apply the rule properly. Apply the sign conventions correctly. Okay, now I'll take B, C, D, B. Okay, B, C, D, B. I'll apply the Kirchhoff's voltage law for this. So I'm going from B, C. Current is also along with me. So I'll take it as I3 times Q. Okay. Now I'm coming like this. Current is opposite to me. So plus I4 times S. Okay. Now I'm going like this. Current is opposite to me. So plus IG times G equals 0, guys. Okay. Now what you can do is, in place of I3 you can substitute, guys. You have already got from the loop rule, junction rule, right? I3 equals I1 minus of IG. Substitute I3 as I1 minus of IG times Q, plus in place of I4 you can take it as I2 plus IG times S plus IG equal into G equals 0. Okay. Now what you can do is, you can take this as equation 1 and equation 2, guys. Okay. Now we have to arrive at the balancing condition. When networks are balanced, when all the four networks are balanced, means when the current through the galvanometer becomes 0, guys. Okay, so that point remember. So what is the balancing condition for a Wheatstone network? Means the IG should be equal to 0. So you can mention here, for balancing condition, okay, that's a condition for the Wheatstone network. For the balancing condition, apply IG equals 0 in equation 1 and 2, guys. Okay, now put IG equals 0 in 1 and 2. What will you get? You get minus of I1P. I'll write it as it is. IG is 0. I will not take this term, leave it. Plus I2R equals 0. Similarly, I'll apply IG equals 0 for the second equation. What will I get? Minus I1 times Q. You just leave this. Okay, even here, delete this. Here I2 is deleted. So what will you get? Plus I2 times S. Again, IG equals 0, deleted, equals 0. You will get it. Okay. Now what you can do is, you can shift this minus to the other side. You will get I2R equals minus I1P. When it goes to the other side, it becomes I1P. Similarly, I2S equals minus I1Q. If it goes to the other side, it becomes plus I1 times Q. Now you can just divide these two equations, whatever you got. Okay. You can cancel I2 and I1 can be cancelled. So finally, what is the expression you are getting? P by Q equals R by S. That's it. Hence proved. So this is the balancing condition for Wheatstone network, guys. Okay, so that's it. These are the derivations what you have in your current electricity chapter. You just check any model paper. Okay, confirm one question from this chapter will be there. Like whatever I did now, confirm one 5 mark or 3 mark, or almost I think I've covered around 7 marks. I think I've covered over here itself. Okay, and if you get it lost in 2-3 marks, again almost 10 marks are covered. Okay, I think this is the most important chapter, guys. So like this, we'll be trying to cover all the derivations from all the chapters. We'll try to cover. Okay, so in case if you have any doubts or queries, please drop your comments in the comment section. Okay, thank you all.